presenter is Mr. Zhao. He's a PhD candidate at the University of Texas Arlington. He received his master's degree in electrical engineering from Eastern Washington University.
That's bachelor. I'm sorry, bachelor degree.
Bachelor degree, and his master's degree from Wichita State University. I let him introduce himself, but I would like to thank you for coming to Alaska and give us a talk today.
Thank you, Dr. Mohammed. First of all, thank you for having me here. Quite excited. This is my first time in Alaska. It's a lot colder than Texas for sure, but I like coldness. All right, so today, what I want to share with everybody here is a development of an IoT-based power monitoring system for the substation of petrochemical facilities. First of all, let me introduce a little bit about my lab, see where I am from. As Dr. Mohammed mentioned, I'm from UT Arlington, and ESRC is the lab where I study. I spent almost 5 years there so far. It has been 50 years. So it was founded by Dr. Mo-Shin Chen in 1968. Now, my advisor, Dr. Wei-Jun Li, he is the director of this lab. ESRC is one of the largest university research centers focused on power system in the United States. And so far, we have worked with many different companies all around the world, as you can see here. And here's a little bit of introduction about myself. I did my undergrad in Eastern Washington, and after that, I went to Kansas. I got my master from Wichita State. Now I'm working on my PhD at UT Arlington. My advisor is Dr. Wei-Jun Li. Currently, I'm an associate editor of IEEE transactions on industry applications. I'm also reviewers for different transaction journals. And my research area is focused on IoT-based monitoring system and demand response. It's more like a electricity market. And arc flash protection in power systems. So far, I have published 10 IEEE transaction papers. I will graduate with my PhD this May, so I'm quite excited about it. Can't wait. All right, so here's a outline of my presentation. First of all, I will give you a background about this work. And I'm going to talk about the mechanism development. And after that, I'm going to talk about application and the conclusion. So background. So based on what I know we have a lot of petrochemical industry in Alaska, right? This is kind of like Texas. So this is a project we did. We spent 2 years on the project. It's designed for a local petrochemical facility in South Texas. The reason we start working on this, if you look at the electricity petrochemical industry they consume every year. So actually they consume 7% of all electricity which generated in the US. And petrochemical industry is the largest energy user in industry. So here's I see how much energy they consume every year. And another thing is they require really high quality power because they have a lot of special equipment. So they require high quality power. And so any blackout and interruptions can cause huge financial losses. Last year, I think the beginning of last year, right? So the company we worked with, I think they had a blackout for 3 days. They lost, if I remember correctly, they lost around $10 million during the 3 days. So it's a really sensitive thing for petrochemical industry. So since this is an IoT-based monitoring system, here's a little background about the IoT. So what is IoT, right? Internet of Things. The definition of IoT is a network of everyday devices, appliances, and other objects equipped with a computer chip and sensors that can collect and transmit the data through the internet. Right? So the key word here is data. So we have to have a data, and basically we play with data here. And the purpose of IoT is to use network to build connections among objects while reduce time and the location limitations, all right? So in power system, what we can do with IoT? So IoT can make power system more efficient, secure, reliable, resilient, and sustainable. So when we're talking about the monitoring system, I think probably the first monitoring system came up in your mind is secure monitoring system. This is a video from my security monitoring system. What happened is this guy stole my Amazon package, and my system recorded everything, right? There you go. Okay, so when we're talking about a monitoring system, what can be a good monitoring system? So here's the thing. First of all, it has to have a triggering functions, like what you see here. He showed up, he triggered the system, and it starts recording. All right. So therefore, we have to have recording functions. And meanwhile, we want to make sure everything can be recorded and stored in a safe place, so that we can dig out later, see what exactly happened. So it has data storage, and appropriate sampling speed. In this case, you want to make sure you can see this guy's face clearly. So that means you want to make sure the data, we can have the appropriate sampling speed. The reason it doesn't have to be a high sampling speed, because you don't want to waste too much resources. And also accessibility and reliability of the system. So for this case, I can see what happened from my cell phone, from my computer. And the last one is security. This is mainly for the power system. I'm going to talk about, based on my project, one by one. As an engineer, when we're talking about monitoring system, SCADA will be the first thing, right? A lot of people ask me, so what's the difference between your system and SCADA? I will explain in a minute. But just give you a background about the SCADA. So what is a SCADA system? SCADA system is a computer system for gathering and analyzing real-time data, okay? And the SCADA system are used to monitor and control a plant or equipment in industries. And the main function of a SCADA system is data acquisition, get data, and network data communication, and data presentation and control. But in my case, since this is a monitoring system, we don't do control. We only do monitoring. And since this is a monitoring system we designed for a substation in a petrochemical facility, when you're talking about a monitoring system for substation, one protocol you have to use is IEC 61850. So this is a substation automation protocol for substation monitoring. The reason they developed this protocol is when you have different IEDs. So if you look here, so they might buy different products from different companies, right? To make they can talk to each other and share the data, they have to find a common platform or protocol, so they can provide a way to let the different IEDs to talk to each other. So this is a IEC 61850. This is the most common monitoring protocol for substation monitoring. And in this case, one of the IEDs I want to mention is DFR, okay? Because this guy can record what happened. If something wrong, this can record the detailed data. The reason I'm talking about this is I wanna show how different our system is from what they already have nowadays. Okay, so what we did is IoT-based FPGA platform monitoring system. This is a platform of our monitoring system. Okay, so let me go through this step by step. First of all, we have controllers. We have two controllers. The reason we have two controllers installed in substation is we want to make sure if one failed, we still have another one running, okay? So we have two exactly the same controllers. In this case, we use a compact rail as our controller, okay? From N9, it's compact rail. And we got a voltage, we record a voltage, we record a power, PQ, we got a GPS timestamp. And all the data collected by the controllers and shared and sent through a hub. Okay, so this is a controller. This is a control piece. This is called host PC. This PC and two controllers, this part are installed in the substation. Okay, this part are installed in the substation, and all the data can be shared and sent to the engineer's office or manager's office. That's what you see here. Okay, and for our system, the company, they don't want us to add this part, internet accessibility, because of the security reason. All right, they never want to share anything with outsider, but this can be added anytime. But in our system, we didn't do this, but they can add it easily anytime. Okay, so let's see what do we have, like as a monitoring system, like how many different types of data we're collecting, we're monitoring. We have a voltage, and the sampling speed is 2,000 samples per second. So that's pretty much like 33 samples per cycle. And we also have frequency. The frequency based on, we got frequency based on the voltage data. We have a P and a Q. The sampling speed is 10 samples per second because it does not change too much. That's why it does not require high sampling speed, 10 samples per second. And we also have a circuit breaker status, also one samples per second for CB status. We also monitor transformer temperatures. And meanwhile, we have a GPS timestamp. Okay, those are all the inputs data we have for this monitoring system. Okay, so next one, let's see what excuse me, detection mechanism we have here. We have voltage detection mechanism. We have frequency. We have a power detection mechanism. We mainly focus on the power oscillation detection. This is about the power stability and circuit breaker status and transformer temperature and SSO monitoring detection. I'm going to talk about this one by one to explain what this is. Okay, so voltage detection mechanism. So our system will detect if something, if the voltage deviation is between 5% to 10%. If this case lasts more than 3 cycles, okay, our system will start recording. The recording period is 2 seconds before and 5 seconds after. Okay, so this is how long we record, because we want to make sure that if something happens, engineers, they can see from beginning to the end. And if it's a deviation higher than 10% and lasts more than 1 cycle, and it's going to start recording. That's for the voltage detection mechanism. For the frequency, as I mentioned earlier, the frequency, we calculate the frequency based on the voltage data. What we did is we can find a period, okay? So we can find a period of the voltage data, and we're using zero crossing method to find, and the frequency is 1 over period, right? So everybody will understand this part. And if it's the frequency deviation higher than 0.2 hertz, that lasts more than 3 cycles, and the system is going to record. It's going to start recording until the deviation less than 0.05 hertz. Okay, this is a frequency detection mechanism. Power oscillation detection mechanism. All right, so here's something I want to talk about, because for most petrochemical facility, they normally have a cogeneration. Right? They have their own power plants inside of their facility. So what happens is when they have their own cogeneration inside of their facility, they normally will connect to the system, the general system. Right? So there's a tie line between their own system and the power system. Right? So what happens is, if they have certain situations like a chain structure and weak connection or imbalance among different areas, or shortage of reserve capacity, or even like interaction with different control devices, it can cause any unstable situations. So in a way to detect this, we want to we will detect this based on the power, right? So power on a tie line. Let's see if there's anything wrong, we're going to detect it. How we're going to do this? Maybe actually add something here. I don't know about Alaska, but in Texas, we have ERCOT system. We have the ERCOT market. the interesting thing about the ERCOT system is, since the petrochemical company, they have their own power plants, they can be part of the system. So they, based on the market price, they will decide whether I will sell the energy to the system or buy energy from the system, or I will generate by myself. So it's called the demand response. Okay, so what they do is when the price in electricity market is high, at this moment, if they can make money, if they can make profit from this, from selling the power to the power system, to the ERCOT system, they're gonna sell their power to the system, right? So they're gonna send the power back to the power system. If at this moment it's cheaper to buy electricity than generating by themselves, they're gonna buy it from power system. That's how they do this. So the company we work for, they're part of this market. They can make a lot of money from demand response every year. So that's one thing I want to mention here. I want to show where this is from. Okay, so here's our detection mechanism. It's called a low frequency oscillation detection. Okay, so when a power oscillation for real power, if it's the magnitude of the oscillation less than 5 megawatt, that means it's normal. And for Q, if it's less or equal to 10, it's normal. And if it's higher than 5, it's going to record. Okay, and between 10 to 20, not just record, they're going to send an alarm to engineers. And what we did in this case, we use transducers. We use transducers to get power. What that means is basically the power signal will be transferred to the DC voltage. Okay, so we got a DC voltage as a power signal, and go through a bandpass filter, and we want to estimate the magnitude. If anything happened in this range, all right, so like higher than 5, higher than 10 for Q, higher than 5 for P, it's going to start recording. All right, that's how this system works. Next detection mechanism is called SSO. I don't know how many of you guys heard about this. It's called a supersynchronous oscillation. So what that means is, okay, so normally in power system, okay, this is we have a generator, we have a transmission lines, okay, and to improve the transfer capacity, right, we add a series capacitor in transmission lines to the compensation. It's called a series compensation. When you put a C capacitor in the system, you have induction in your system, right? It's transmission line. When you have L, when you have a C, what you're gonna have? You're gonna have natural frequency. Okay. When you have a natural frequency, when a natural frequency the same as mechanical frequency in your generator, it's going to oscillate. Okay, that's the basic definition of SSO. SSO and SSR. So when it starts oscillating, it doesn't mean they're gonna. It doesn't mean they're gonna resonate. But from SSO to SSR, it takes time. So sometimes people misuse these two words, actually. Sometimes they use SSR, SSO, SSO, SSR. Nowadays, we even have more different terms. For example, we have SSCI, we have SSTI for different situations. But SSR is defined as the resonance between a series capacitor compensated electric system and the mechanical spring mass system of a turbine generator at the subsynchronous frequencies. Okay, it's not a new thing. It's not a new thing anymore. The first SSR happened in Mojave Power Station in 1970. So far, there are a lot of studies have done about this. We just add this to our system because the reason we want to do this is in Texas, we have a lot of wind power. When you have a lot of wind power, we might have SSCI. SSCI is a type of a sub-branch of SSO or SSR. Okay. This is what happened in ERCOT system. After SSR happened, you can see the current starts oscillating and gradually goes up, and this is the voltage, right? So this is gonna break the generator, destroy a lot of devices. And in our system, we actually adopted a mechanism from a current industry. Here's what we did. Okay, here's what we did. First of all, we did a demodulation. So here, let's say if this is a voltage, right? So we want to demodulate the signal. So what does that mean? We found upper envelope here. We found a lower envelope here, and we use upper minus a lower. Okay, and we apply I5T to the demodulated signal, and we can find a dominant oscillation frequency. Right. So this is from the current industry method. After this, because this work was from 1 year ago, 1.5 years ago. After that, my lab mate and we even developed a new mechanism. If you're interested, actually this method is way more faster than what they have. If you are interested, you can check this paper. It has been published. Okay, the circuit breaker status. So this is really straightforward. So if any circuit breaker trip, you will see something like this. All right. So like what time, right? What its action is either closed or open. It's really straightforward. So basically, you can tell the status of the circuit breakers. Okay, we come to here. Task allocation and process. Actually, this is the most challenging part for this monitoring system. We spent, I think, 3 months to adjust this part. In the beginning, let me do this. Let me talk about this one by one. Okay, so this is a controller I mentioned. All right, so compact rail. We have two compact rails, and we have different modules installed in compact rail. Each module does different things. We have analog input, digital input, GPS, blah blah blah. So okay, we also have FPGA. How many of you guys know what FPGA is? Okay, FPGA is a field programmable gate array. So what is FPGA? All right, let me put in a simple word. FPGA is just circuit. A circuit we can program. All right, so that's why it's called a hardware programmable device. So basically, we can program FPGA, but it's hardware program. And the advantage of FPGA is it is really reliable, and it's fast because it's just circuit. Right? It's just circuit, fast and reliable. So based on this, we want to make sure. So we want to apply data acquisition with FPGA. So in this case, we use FPGA to do the data acquisition. We also apply the detection functions on FPGA. Since FPGA can be programmable, can be programmed, so that's why we put a detection function on FPGA. This controller also has CPU. Okay, so we put a data logging on CPU. We use CPU to do the data logging. The reason is we cannot really use FPGA to do the data logging. There is a limitation for FPGA. The last part is report generation. So if anything happens, engineers, by the end of the day, you want to see what happened, when that happened. So we also have a report generation. So in the beginning, we put a lot of, what we did is we put the detection functions on CPU, but we realized that is not the best thing to do because CPU is not deterministic. Since it is not deterministic, that means the result is not that precise, it's not accurate. So we changed everything, we moved everything back to the FPGA. We only left the data logging on CPU. Basically, we did back and forth, we tried different things. Eventually, we make the system work evenly. And timestamp and synchronization. As an IoT-based system, the synchronization is one of the most important things for the system. Nowadays, are using NTP, right? So it's called Network Time Protocol. But in this system, we cannot use it because of a security reason. So what we did is we have a industrial standard GPS, right? So this is really accurate. I think the accuracy is 100 nanosecond for this module applied. And here's what we did for the timestamp. We got a GPS module, so we can have a timestamp. We can timestamp from the GPS module. If you remember what I mentioned in previous slide is we got the data, we did the data acquisition with FPGA. So when we get the data from FPGA, as you can see, here's FPGA. We got a timestamp, we got the data here, different data. We basically timestamp everything on FPGA. So one data, one timestamp, one data, one timestamp. So make sure everything is precise. Okay, that's what we did. Okay. When we're talking about the IoT system, one thing we have to pay attention is cybersecurity. So in this system, we applied hardware firewall to make sure it's more secure. And we also applied DMZ. DMZ is called a demilitarized zone. What that means is, as you can see here, right? So we have a two hardware firewall, and we have our system here, controller. We have a NAS, and so NAS is more like a hard drive. So if something happened, all the data will be recorded here. Okay, all the data will be stored into the NAS. So the thing is, if people outside of this hardware firewall, you want to access the system, the furthest they can go is this. It's more like a buffer zone, right? They cannot go inside. They cannot control controller or NAS. They cannot dig in. The only thing they can see, right, they can break in is DMZ. That's why we add this part to make sure it's more secure. Of course, we add a password and a username for this system, so only authorized people can access this system. Here's the in-lab setup. So this is what compact real. Okay, this device is compact real. Okay, controller. We have different modules. Right. So basically, based on your need, if you need something different, you can buy different modules. Okay. And here is the mini system. We did a test in our lab. We have 4-bay NAS. This is like hard drive, right? So if something happened, all the data can be stored here. We have hub, we have two controller. They're doing exactly the same job. That means if one fails, another one still keep running to make sure the system is more secure. We use DC power source to test the power oscillation, if you remember. Yeah, here's the GPS and antenna. This is what the system looks like. To do the SSO detection, we did a simulation with this system. We added a 37.5 hertz signal to the 60 hertz signal. As you can see, after we add this signal, the voltage starts oscillating. You can see this up and down. And the system detected after 354 milliseconds. So everything went really well. This is a front panel for engineers. Basically, as an engineer, this is what they see every day. Okay, I blocked certain names because this kind of confidential information they don't want me to share. What you see here is, so this is more like a framework of that substation. Those are transformers. You can see voltage, frequency, power, PQ, and this green one is our circuit breakers. If anything happens, it's going to turn red. And these are two tie lines connected to the power system, right? So these two tie lines connect to the ERCOT system. In this system, we also did like alarming functions. So if something happened, they can see it. Not only see, they can hear it. There's a sound alarm also. They can see there's a sound alarm. Because this is a huge system, we spent 2 years to develop this system. So there might be some error inside of this system. So to differentiate the alarm from the substation and its own problem, we also have a self-alarming function. So if something happened, we can see that because we can debug the system. Uh, and for the data logging, so here's one example. I just took one from the data logging part. I want to show you guys if something happened, what kind of data we have. We have timestamp, and this is the raw data of the voltage. You can see here, and this is the frequency. Frequency and RMS in this system is calculated based on cycle. That's why we have only one here. So we calculate based on cycle by cycle, not sample by sample. It's cycle by cycle, right? So here's a data logging file. This is the only picture I took in that substation the system installed. Okay, because we cannot share more information with you guys. Sorry, but this is a picture we took in that substation. You can see there are two controllers, a whole bunch of wires. Actually, it took us 3 days to install this system, to test it, to install this. It's a lot of work. And after the system installed in 2018, August the 1st, not too long after the system installed, something happened in that substation. And it's a under voltage event on phase B of the 138 volt line. What happened is our system captured this. All right, so this from two controllers. You can see they recorded exactly the same thing pretty much. And all the detailed data were recorded with timestamp. Probably you will see you're confused with all these big numbers. Why is it like timestamp or all this? Those are epoch time. So that means it starts, the reference starts from January 1st, 1904. Okay, that's why you see there's huge numbers here. We captured this, so engineers took all the data out, compared with the DFR. We actually have a lot more detailed data compared with the DFR. And because we have a longer recording period, they also can see some other information from our system. So as a conclusion, with this IoT-based power monitoring system, we enhance the data acquisition speed and system computing power significantly to provide real-time data precisely. So everything in this system is real-time, since this is IoT application. And the IoT platform provides flexible system accessibility for system operators so that they can visualize the condition of the power system in real time. And all the necessary data can be recorded based on the triggering mechanisms for further analysis, and engineers and the system operators can have much better understanding of the power system operation inside of that facility. And also this lossless data logging feature with high resolution sampling and timestamp provides detailed information for the system operators so they can help them to improve the overall operation. Let's get back to the question I brought up in the beginning. So how different this system is from the SCADA system? First of all, the normal SCADA system, the sampling speed is 1, 2, 3 samples per second. So it's quite slow. So our system a lot faster, okay? And another thing is, if you remember, in previous slides, I put different IEDs there, right? So when the companies, they want to have different features where they want to monitor different things, they have to buy different products, right, to realize certain functions. But with this system, actually, they can change it, they can modify it anytime they want because FPGA is programmable, right? So as long as they have the data, it doesn't matter how they want to play it. So in this case, if you remember, we have certain different detection functions. Let's say someday they want to change it. They can reprogram it to change all the detection functions, redo everything. So it's more like a cost efficient. Yeah, here's all my presentation. There's a picture of that petrochemical facility we went down in South Texas. Really nice place, close to the ocean. Here's my presentation. Please let me know if you have any questions or comments regarding this project. Yes.
So did the higher speed data help them out on that under voltage event?
I think I have to repeat the question. Sure. So did the high-speed sampling data help them with the post-fault analysis? Yes, it helped, because For the reason, because, yeah, for in that facility, actually, when I went there, I was kind of shocked because I the control room, they have a different monitoring systems. Actually, not only one, not two, they have three. What they want to do, they want to make sure if something happened, they want to make sure they can have a one reference to compare with. So for them, the DFR recorded everything, surely, but it's with a really short period. Our system has a long period signal. So they compare with what we have, they found out what the problem is. Yes, it helped. Yes. Yes, sir.
Yes. So is there a central control station where all this data gets fed to, where operators are monitoring it?
Yes. Everything.
Data transmitted by, how is it being transmitted? By Wi-Fi or fiber optics, or how is it being transmitted?
Local area network.
Okay.
Yeah.
So it's a hardwire.
Hardwire.
How come they don't use the Wi-Fi?
Security reason. They don't want to use Wi-Fi because of the security reason. Yeah. Mm-hmm. Yes, sir.
Can this system be applied to some other industries?
Oh yeah, absolutely. This system, we actually developed another. The question is, can we apply this to other different systems? We actually applied this. We changed something. All right, we applied this to monitor wind turbine. We still use the basic framework of this IoT thing. We apply this to monitor the wind turbine, and there's a paper has been published. If you're interested, I can share with you. Yes, it can. That's why I say this system is really flexible. The one thing I love, before this, I never deal with FPGA, all these kind of things. But after this, I think this is a really good way for industry to do anything they want, pretty much like monitoring control. This can be even applied as a controller. I mean, really control something. But in this case, we didn't do that. Because FPGA, first of all, is really reliable. And it is also deterministic. Deterministic is really important for a real-time system, right? That's really, really important. Deterministic is really important. So, also reliable. And so there are a whole bunch of advantages for FPGA. So anytime you want to change anything, you can go inside, change it, reprogram it. So it's really a good way to deal with this. Yeah. Any other questions? Yes, sir.
So it's interesting they sell power. How far out do they dispatch that? What are the time cycles? Will they go from buying or selling power to ERCOT?
For ERCOT?
Yeah. I mean, do they have to plan? Is that days ahead?
Oh, no. Oh,
Buy to sell frequencies.
from buy to sell, what's the frequency? They have different types of. They have day ahead. They have real time. They have 15 minutes. They have hourly market. They have 15 minutes. They have real time. So in this case, actually, it depends on how you want to play. This is just like a game. Depends on how you want to participate the market. For them, I think for sure they're part of a real time market because last August, what happened in ERCOT system is the price of the electricity goes to $9,000 per megawatt hour. $9,000 per megawatt. That means $9 per kilowatt hour electricity, because it's really hot last summer in August. So if they bid and if they sell power at that time, they're gonna make a lot of money. So that's real time market.
And that's like a 15 minutes?
That's 15 minutes. Yeah.
They'll do a price update.
Yeah, they will do. Actually, you go to ERCOT market, you will see every 15 minutes they're gonna, yeah. And one thing I love Texas is we have free electricity. The really free electricity. I am one of the users it's called nighttime free electricity. You can have 9 hours free electricity. You can either choose from 8 p.m. to 5 a.m., 9 to 6, or 10 to 7. So during this time, electricity is free. It's really free. That's why, like, for me, it's really good because I go back home during nighttime. I do everything at nighttime. So everything's free for me. Yeah, AC, everything's free. So think about if you have EV or you want to charge your EV during nighttime, it's also free. Yeah, because they have a lot of wind power during the nighttime. Normally, the wind generation at nighttime is higher than the daytime, normally. Yeah, that's why they can have certain program like this in Texas. Yeah. PMUs? This one? Yes, it is. This system, actually, if you compare with the PMUs, right? PMU, I don't really know about the detection functions for the PMUs. But as I mentioned for this one, if you look at this system, it's a complete system from data acquisition all the way to report generation. Okay, so this is like complete system. Yeah, you can say certain part of this system can be replaced by other devices, but this whole system is complete from data acquisition, all right, detection, and data storage, data logging, and to all the way to report generation. So this is a complete system. That's one good thing about this one. Yes, sir.
System cost compared to SCADA, I guess.
Oh, the question is the cost of this system. The controller itself plus the modules, I think around 20K. Yeah. So no SCADA way more bigger than this is mainly focused on substation monitoring, but SCADA normally is for like huge power plants or something like that, right? And actually, I don't know if we can compare the cost with the larger system, because this is more like a scale system, but with a faster sampling speed. Yeah.
There is no question, so this is your thank you.
All right, thank you. All right, thank you for having me here.